This is a quick introduction in how to use the Hydra and Medusa combined software packages to calculate and predict and produce things like fraction diagrams and predominance diagrams for speciation, both of metal ions and anions. So the first thing is to open the Hydra software. You will get a periodic table that looks like this, very intuitive. You now just need to select what you want in your system. And we call those things components. And you can select anything from the periodic table. And what you have in this right area, this box says components selected. Those are the things that you've chosen. By default, they're going to include protons, which means that by default, the system is going to be modeled in water. You would have to select this and delete it. Click yes if you wanted to do this in a non-aqueous system, but we're going to do it in aqueous systems for the most part to start with. So for example, let's start with the selenide system. So if I click selenium from the periodic table, I'm going to be given 3 different versions of selenium that I can choose as a component. And this is really important. These 3 species all have different oxidation states. That's why you have 3 of them. This is the version I am interested in because this is the selenium version that is going to be modeled as H2Se, HSE, and just the selenide ion. These other ones all have different oxidation states. So there will only be one component representing each oxidation state. So I'll select that. And that doesn't mean I'm only modeling HSE minus. It means that this is the component that I'm selecting, and it will include all of the possible species of this oxidation state, which means the fully protonated version and the non-protonated version. So this is all I need to fully model the selenium anion system in water. So the next step would be to go to File, Save and Exit, and then I'll choose this Save File and make a diagram with Medusa. So I will be prompted to save this. I'll save it just as SE for now. I'll choose Save, and this will prompt the opening of a separate software package that's linked. It's called Medusa. So Hydra is essentially just a database of equilibrium constants. So when you select something from the periodic table, it just pulls up from a database all of the relevant equilibrium constants associated with that component. When you want to actually plot this as a graph, then we use Medusa. So once I'm in Medusa, the data file will automatically load, so you don't have to do anything. All you have to do is go to Run, and then make a diagram, and we'll be prompted with this select diagram type interface. And so this diagram dialog here in the center shows what we want on a y-axis and on our x-axis, and then in the center here it shows what diagram type. The diagram type is where we can choose a predominance diagram or a fraction diagram. We can choose log C diagrams, which we may or may not use in this class, but are used extensively in things like environmental chemistry, analytical, geochemistry, etc. We're going to start with a fraction diagram. And notice how that prompted me to have a selection for my y-axis, so I can either choose to plot, in any case for a fraction diagram, I'm going to plot 0 to 100%, which is going to represent which species is dominant and at what percentage, and I can choose which component I want to plot. Of course, I don't want to plot H+, which is essentially pH. I want to know what species of selenium is dominant as a function of pH. And so on the x-axis, I'll leave it as pH varied and H+ here, and then down here I can choose and edit what my total concentrations are. And for most of the predominance diagrams that we're dealing with, in the simplest versions of them, we're assuming them to be at 1 molar. So I'm just going to throw 1 molar in there. That's a standard state condition, so it's always a good approximation, though in real world systems, natural systems, you almost never have 1 molar, you're much lower concentrations. That will factor in when we start to think about a predominance diagram. And then I can change the range at which I plot this pH over. So maybe I'll go from -2, and you're not constrained to 0 to 14, so maybe I'll go up to say 16 here and then click OK. Less relevant right now, but maybe later or in other courses, I can change the ionic strength, which changes the activity of these concentrations. But I'm not going to do that now because it's not important, because I want just the thermodynamic steady state conditions. So at this point, all I have to do is click make the diagram. That's going to plot this. It's going to prompt me here before it executes. It's going to say, you have a pretty big range in your pH that's sort of not outside of the normal range. Are you sure this isn't an error? And I'll just press enter, and now it will have plotted my fraction diagram. And so the fraction diagram, you can see that the total component concentration, that means all the species of selenium, add up to 1 molar. So at any given moment here, all of the different 3 species of selenium are going to add up to 1 molar. Fraction here is from 0 to 100%, or 0 to 1. And then we have pH over the range that we decided to plot. And so you can see at most acidic pHs, we of course have the fully protonated version, and then that starts to decrease as the pH becomes more basic. At the same time, we have an increase in the amphiprotic species as we start to deprotonate that until the 2 lines intersect. We know that at the intersection, the fraction is 0.5 and 0.5. That means they're equal to each other. That's the point in the Henderson-Hasselbalch equation where the log term goes to 0, and we know that the pH is equal to the pKa. So the pKa of this system is exactly at this intersection, which we could just, by visual inspection, read directly from here. Increasing the pH further then starts to dominate this species. At the same time, we start to decrease the concentration of this species. And then, of course, as we keep going, at some point, we reach the next pKa, which means we drop that second proton. That pKa is at the next intersection, which is occurring here. Most cases, you'll probably just read off this directly or go to menu and copy to clipboard. You can paste this into PowerPoint or Word file and read this off directly. You can also regraph this with different parameters. I just close this. I'm going to still be in Medusa, so I'll go back to run, make a diagram. My values will have been saved, but if, say, I wanted to extend my pH range, I could go in and edit those or change my concentration, whatever I want, I can do that. So in this case, let's make a predominance diagram. And so in the predominance diagram, what we can change is actually make this a 2-dimensional plot, in which case we're varying the concentration rather than fixing it at 1 of the component and then still plotting it over the varied pH range. And so let's just leave it as default here, but note that these are log concentrations because these are going to be pretty significant differences in ranges, and it's going to plot from, let's run this all the way up to 1 because that is the same as 1 molar. So we're at 1 molar way up here, and we're at roughly 1 micromolar down here. And so we're going to look at the same speciation, but we're going to do it as a function of concentration. It's going to prompt me for the same thing. Now it's going to compute it, and we're going to get a graph that looks something like this. So now I have log concentration, that's the total concentration of my species. Now I can see what those things are as a function of concentration. Turns out that for anions, it's nothing special, but for cations, we start to see a significant effect here when we get to more and more dilute systems, which I'll show in a separate video.